Keith here with another statistical video, and this one's going to be quite short. I'm going to look at the problem of doing multiple t-tests to compare samples. When we do a single t-test comparing the means of two independent or unpaired samples, the type 1 error rate is 5% or 0.05. That means if the null hypothesis is true, the chance of making a type 1 error is 5%. We should on average make about one type 1 error in every 20 tests. Now up here on screen I've got a little Excel simulation where I'm simulating taking 10 samples from the same population, and you can think of these as 10 women because the mean and standard deviation I'm using here are the mean height of Australian women and the standard deviation for that population. So it's just the same as if I went and randomly took 10 samples of 10 women. You can see for each sample I'm calculating the mean and standard deviation, and these are coming in sometimes lower than the population value of 166 for the mean and 7 for the standard deviation, and sometimes higher. That's due to normal random variation. Under the data, I'm putting the results of tests, t-tests, independent t-tests comparing the samples. So the top row is comparing sample 1 to every other sample. You can see they're all non-significant. Next is sample 2 or all others, and they're all non-significant. If I scroll down a bit, in here I'm calculating the actual probabilities associated with that particular calculated t-value. I'm not displaying the t-values, they're not very meaningful. And you see all the probabilities are greater than 0.05, so all the tests are non-significant. What happens if we repeat this a few times? 1, 3, lots, 3, 4, 5, 6, 7, 8, 9, 10 of the tests are significant. 2, 3, 5, and so on. You get the idea. Another case where we're making lots of mistakes, and this will be due to some samples being very unrepresentative, so the numbers here are coming out quite small. This mean is 162, so 4 centimeters smaller than the actual population value, and some, such as this one here and this one here, are coming out rather larger or higher than the population value. However, it's pretty clear that it's easy to make lots of mistakes, so that's why an omnibus test, a test that compares all samples at the same time, like analysis of variance, is a better option. And if we reject the null, we can pursue other alternatives such as multiple comparisons procedures like Tukey's test or the Bonferroni correction, although the Bonferroni correction is overcorrecting. What's the actual chance of making at least one mistake in this set of tests? Well, to do all the comparisons, there's a total of 45 tests. And so the probability of making at least one mistake is 1 minus the probability of not making a mistake in any of those 45 tests. So if the null is true, which it is all the time in this simulation, it's 1 minus 0.95 to the power of 45. And that comes out at a little bit over 0.9. So there's a 90% chance of making at least one type 1 error in comparing all these samples. So, get busy doing ANOVA.